Good afternoon. Welcome to the last session of the day for this first day of Flash Memory Summit. My name is Curtis Ballard. I'm a distinguished technologist with Hewlett-Packard Enterprise, and I have with me today Eric Smith, who's a distinguished engineer with Dell Technologies, and we're here to talk to you about discovery automation and centralized discovery for NVMe over fabrics. Eric is up first. Well.
Thanks, Curtis. So we're going to start with an overview of NVMe over fabrics technology and get into a little bit of discovery. Also talk about direct versus centralized discovery details, and then give you a centralized discovery walkthrough. So NVMe over fabrics discovery is built around discovery controllers. And if you don't know this, a discovery controller is a single location that reports all NVM subsystem interfaces. The discovery controller simplifies administration because a single discovery controller IP address can provide connectivity information about multiple subsystems and their interfaces. Another big thing in NVMe over fabrics is the concept of a referral. And a referral is the ability for a discovery controller to refer to other discovery controllers. Now, a common implementation today is that every storage subsystem or array contains a discovery controller that only describes the interfaces on that subsystem. And I know certainly Dell's subsystems are that way, and I know many others are as well. And so until recently, and the reason that a lot of the work that Curtis and I have done together over the past 2 years and we'll be describing is that there was no standardized method for hosts, subsystems, or discovery controllers for that matter to register information with a single discovery controller. And that's how Fiber Channel works and is one of the things that we were trying to emulate. So the centralized discovery controller section is going to cover this in a bit of detail. Before we get there, let's talk about some basic NVMe IP SAN terminology. There's this thing called the centralized discovery controller, or CDC. The centralized discovery controller is a discovery controller. It just happens to be running, not on a subsystem necessarily. It's typically running in a VM or on a switch or as a collection of microservices somewhere. It could even be running on a DPU if you wanted it to. But the idea is that it provides fabric services that can be used by hosts and subsystems, which we refer to as endpoints. Now, endpoints are identified by NVMe qualified names, or NQNs, and their IP addresses, which is optional. There's also, of course, these endpoints are connected over an IP network. As we're thinking about NVMe TCP specifically, we've been looking at mostly 25 gig platforms and above. There's also this concept of a subsystem, and if you're from the SCSI realm, you'd probably think of this as a target. And again, subsystems are storage arrays. You identify them by NQN and IP address. And again, the NQN is similar to a worldwide port name in Fiber Channel or an IQN in iSCSI. The CDC, in this case, centralized discovery controller instances think of them as shards of the CDC that are associated with each IP SAN. And an IP SAN is a collection of one or more subnets that are supposed to have NVMe traffic flowing over them. So each CDC instance is associated with exactly one IP SAN. And then a direct discovery controller, this is the discovery controller that resides on a subsystem, so on the array. And hosts, by the way, can connect directly to storage via this direct discovery controller. If they wanted to, they can discover all the subsystem interfaces on that array, but you lose the benefits of centralization if you do it that way. So when we first started working on this project, we wanted to make sure that we supported 3 basic types of physical connectivity options, or deployment types rather. And the first one was direct connect. That's physically connecting your host and storage together over a cable. And the reason that I was very concerned about this was the work that we had done with FCOE when it first came out didn't support this type of connectivity, and we wanted to make sure we didn't repeat that mistake. Direct discovery was the next one that we really wanted to make sure we supported. This is all hosts and subsystems connected over an IP fabric without a CDC in it. So just regular direct discovery controllers only. And then the third type was a centralized discovery where we had a CDC and DDCs in the environment, and the hosts could use the CDC to discover the storage ports on those subsystems automatically, and we'll get into how that works. Before we talk about centralized discovery, let's talk about how discovery was done previously. Now, when NVMe over Fabrics was first standardized and released, this was how discovery was basically performed. The host would send a connect, or the host administrator would send connect to the discovery controller at an IP address that would be supplied by the admin. And the purpose of doing that connect, it's not strictly required, but the reason you would do it would be to avoid having to figure out what the NQN of the host was, and then typing that in manually to the subsystem as you're going through the process of provisioning namespaces, which is the next step. So the next step is for the storage admin to provision namespaces to that host NQN. And once that's done, you could go back over to the host and have the host admin use NVMe connect all or something along those lines to discover and connect to all of the I/O controllers on that subsystem. And next, you get to repeat those steps on every host for each subsystem that the host will access. And that's a lot of work, especially as you start to scale these environments up. And I'll have a slide in a minute that will show you just how poorly it scales. Now, with centralized discovery, again, this is the thing that Curtis, myself, and many, many others have worked on for the past few years. This is a new concept. And so we have a centralized discovery controller added into this configuration. And the neat thing about it is when you first bring up your interfaces on your host or subsystems, they automatically discover the CDC. We've defined that a couple of different ways you can automatically discover that the CDC using either MDNS or DNS. But the idea is that you discover the IP address of the CDC, you connect to it, and register discovery information with it. And once that happens, the SAN administrator can go to the CDC and perform zoning on it. When I say zoning, it's a fiber channel term. It means you're connecting host NQNs and sub NQNs together and allowing them to discover each other. And I'll get to why that's a beneficial thing in a minute. But it's optional in this case because one of the things that we did when we were standardizing the CDC was to define that subsystem-driven zoning, or the ability for the subsystem to send zoning information to the CDC automatically, was a part of the standard right from the get-go. So that's a feature that's available. If you have a CDC in your environment, they're actually required to support this. So storage admins would then provision namespaces to the host NQN, and again, the storage may send zoning information to the CDC. Now that zoning information is there, an asynchronous event notification would be sent out from the CDC to the impacted ports. In this case, it would be anybody that was zoned to have access to that subsystem, and then go ahead and use get log page, figure out what I/O ports are available for it, and then go ahead and connect to each I/O controller. And again, the subsystem admin could literally sit there and provision storage to NVMe hosts, and they would be automatically notified and would automatically pick up their storage. There's a huge benefit here in terms of a workload on the admin, and that's why this is really interesting. That's one of the reasons why this is interesting. So if we compare direct versus centralized discovery at scale, one of the things that you'll notice is that I've got sort of number of hosts on the x-axis, and what I'm plotting is the number of configuration steps for direct, which is the red line, and centralized, which is the gray line. And I think it's a judgment call, but I think basically direct discovery starts to get a little bit impractical around 64 hosts, although it's kind of hard just to base that on the chart. But some of the other things that the chart doesn't show that you need to take into consideration is that direct discovery requires interaction with each host every time a storage subsystem is added or removed, and so you got to go to every host, and so it's what I call it's endpoint centric, not network centric discovery. Another thing that the chart doesn't show is that direct discovery may lead to extended discovery time if many subsystem interfaces are present. So why is that? Well, without a centralized discovery controller, every host is going to discover every discovery controller and will need to interact with all of the discovery log page entries that comes back from that discovery controller, which can be dozens from every subsystem. And so you get into this full mesh discovery, waste a bunch of resources, and it takes a lot of time to get through that. So not an issue with the CDC if you've done zoning. So some additional points about discovery automation in general. Just keep in mind that discovery automation does not depend entirely upon centralized discovery or the CDC. Smaller scale environments can use MDNS, as we describe in TP 8009, which is a technical proposal that we worked on with NVM Express, to automatically discover NVMe discovery controllers. But the problem with MDNS is that it does not allow for centralized control. And of course, this means access control of the network is much more complicated. I think it's bordering on impractical. Host will not be notified when a new storage subsystem is added to the environment. That's another downside. And then MDNS has been known to become excessively chatty in larger configurations, especially when there are more than 1,000 ports in a single broadcast domain. This is based on test information that we have found in our environment. So with that, I'm going to turn it over to Curtis for a little bit of more information about centralized discovery and how that works.
Thanks, Eric. Okay, so centralized discovery. Eric introduced the concepts of centralized discovery. I want to talk a little bit more about discovery information. Eric talked about the discovery log pages. The discovery log pages are the mechanism that is used over the NVMe interface to report the discovery information. In the spec, we talk mostly about sharing discovery information. And that discovery information comes from a NVMe storage system. In this example, I'm showing an NVMe storage system here that would probably be a storage array that virtualizes a bunch of NVMe subsystems. That storage array would have the discovery controller, called the direct discovery controller in the centralized discovery terminology, that would list that there are 6 different discovery systems there, and that discovery information would be available over the network via those discovery log pages up to the hosts. The host would connect to that discovery controller and find out there's 6 different systems here. Now, as Eric talked about, there's a scaling problem. This is kind of a graphical example to try and show that when you have a large number of storage systems in an environment, with the direct discovery model, a host, in this example, host A, has to go out and create its own discovery connection to every single one of those storage systems, find the discovery information, and then it has to go connect to all of the subsystems underneath of those. And that turns into a lot of system overhead. When you're trying to do something like NVMe over Fabric boot, the startup time to find all of the subsystems is pretty lengthy and can be troublesome. So the solution we've worked on, as we've talked about, is centralized discovery controllers. Eric's introduced this pretty well, so I'll fly through this slide here. It's the single Fabric entity that aggregates the information. It's a standard API for getting the information to the hosts and for systems to load that information. And it brings in a little bit of new functionality that wasn't in the previous NVMe over Fabric's discovery model, and that is a mechanism for hosts to register host information into the discovery controllers so that your storage fabric can learn about all the hosts that are connected. And it introduces a mechanism for sharing connectivity rules, which we call fabric zoning. If you are familiar with Fiber Channel, the zoning concept should be one you're familiar with and hopefully comfortable with. So what changed for the hosts? The most important thing was this is a clean evolution of existing host discovery. You can take a host that doesn't support centralized discovery, point it to a centralized discovery controller, and it can understand all the information it gets back and connect to the systems out there without even knowing that that's happening. But there is some additional capability that allows the host to register with the storage fabric that provides a little bit more information when the hosts are centralized discovery aware. So as I've said, it's the exact same information. It's just now centralized. Multiple NVMe storage systems all report their 4, 5, 6, however many different NVMe subsystems up to the centralized discovery controller. Aggregated information goes up to the hosts. Exact same format the hosts were used to before. So now we get the situation where storage systems from different vendors can play nicely together. I kind of created this example of representative of my house. You got the cats, you got the dogs, and you got the mice. And the cats and the mice don't play well together. The dogs and the cats don't play nicely together. But by following the standard protocol, everybody's able to register with the centralized discovery controller. And each host only has one connection now to the centralized discovery controller instead of every host connecting to every storage system. I actually drew a diagram that did that, and you couldn't see anything in the middle because of all the lines. So we mentioned the host registrations. We ended up having to do a couple of different models here. We've been asked this a couple of times. For host registrations, there are different architectures that needed different capabilities. And so we've defined a model called push registrations and a model called pull registrations. The push registrations are proactive registrations from the host or a storage system into a centralized discovery controller. That's the only registration model defined for hosts. Hosts are always an initiator pushing data. Storage systems aren't always initiators pushing data, so they can use a push model to push their information into centralized discovery controller. We also created a mechanism called pull registrations. This is only for the centralized discovery controllers. When you hook up a storage system, it will register with the system and request that it wants to use pull registrations, and then the centralized discovery controller uses get log pages and pulls all the information out of the systems. Here's an example, simple centralized discovery sequence. We don't have time to go through this in a lot of detail, but flying through the steps, you can see the host and the storage systems discover the centralized discovery controller. Eric mentioned this briefly. There's a mechanism that uses MDNS, and we've defined mechanisms that support having a simple MDNS responder so we can work across multiple subnets. So you plug the systems in, they use the MDNS discovery model defined in NVMe Proposal 8009. They find each other. The host and the storage systems register with the centralized discovery controller. They read their discovery information from the centralized discovery controller. Then the host can connect to the NVM subsystems, find the namespaces, and start using them. But what about the CDC filtering responses by hosts? One of the things that's implemented today is that the direct discovery controllers can look at a host and say, hey, I only tell you about these specific subsystems. We still need that capability, so we've implemented a model called fabric zoning. It leverages heavily from the fiber channel zoning capabilities and provides a way that you can put zoning information into your fabric that describes which hosts are allowed to connect to which NVM subsystems. Whirlwind tour to how fabric zoning works. You create a zoning database in the centralized discovery controller that it stores information about two different zone types, configured and active zones. The configured zones is a list of zone groups and zone aliases, and then active zones is the zone groups that are being enforced. And dropping down into what those zone groups are, they're the zone members. That can be hosts, NVM subsystems, zone aliases, and you can identify it by all kinds of different methods. NVM NQNs, NVM NQNs with IP addresses, NVM NQNs with IP addresses and port IDs, and all of those are implementing models that we have customers using today. So it looks like there's a lot of different options there. There are a lot of different options, but that's to meet real customer use cases that are served by existing fiber channel systems. And with that, Eric's got an example of NVMe IP SAN operations.
So just bringing everything together, giving an overview of how all these things work together. Start with some NVMe TCP hosts down on the left-hand side, NVMe TCP subsystems on the bottom right. We've got an IP SAN fabric in the middle. It's a leaf spine. And one of the first things that you've got to do when you're creating a fabric is you've got to get those switches to communicate with one another to enable IP reachability between any ports on that fabric. And so in general, there's different every vendor has different functionality that would allow you to create a leaf spine based on maybe some defined policies. And so that would be the very first step, forming your IP SAN fabric and enabling IP reachability between any two endpoints. Next would be for the subsystems and the servers to discover the CDC. And again, Curtis mentioned this. MDNS would be, would probably be what we would use. DNS is also a possibility, but you need to get the IP address of the CDC in order to interact with it. So once that happens, the next step would be for the servers and the storage systems to register with the CDC. And as Curtis mentioned, the host would use a push registration mechanism. The subsystems could use push or pull. And that information would eventually get up into the CDC and be available for the admin or an orchestrator, for that matter, to read the CDC name server database and then set up the appropriate server and storage zones based upon how the customer wants to use it. So once that's activated and you activate the zone database, again, the next thing that happens is for the CDC to notify the server and storage subsystems of a zoning change, and they do that with the asynchronous event notification. That asynchronous event notification causes the end devices to go ahead and send a get log page to the CDC. The CDC comes back with a list of discovery log pages that are accessible to that host, for example, and then the host will go ahead and set up connections from itself to the storage ports that it should be communicating with, and discover the namespaces, and then start transferring data. And that's sort of how everything comes all together, and how we automate discovery with an NVMe SAN IP, with an NVMe IP SAN.